as promised, here's an example that's broken down more into parts. So we have 4 long straight wires. They each have the same current, 350 milliamps. These currents are out of the page. This current is into the page. The wires are 3 meters long. So there's our setup. These are wires with current flowing out like this, and in like that. Part A, draw the magnetic fields at wire 2, so at this position, due to each of the other wires 1, 3, and 4. I've got a new slide for those drawings, so we'll come to here. So I want the magnetic field at wire 2, starting by thinking about the magnetic field due to wire 1. So the magnetic field around wire 1 is a big circle around wire 1. Looks something like this. The magnetic field at wires, so the direction of those circles, we use our right-hand rule. Thumb is our current. Our fingers are coming up this way. Our magnetic field right here is a tangent to the circle, which is going to be perpendicular to the radius of the circle. It's going to point straight up. There's our magnetic field, B1. I forgot to say the dimension of the circle, or the dimensions of the square. I'm going to call that A equals 25 centimeters. And these are arranged on a square, so this is also A equals 25 centimeters. Okay, so there's our B1. I drew that first wire. Now I'll draw my magnetic field due to wire 3. My magnetic field due to wire 3 is big circles around the wire. I draw a circle so that it cuts through wire 2, so that's where I'm trying to find the magnetic field. The direction of the magnetic field, I use my right-hand rule, comes around this way. Then my magnetic field here needs to be a tangent to the circle or perpendicular to the radius, and needs to come to the left this way. So there's my magnetic field, B3. Okay, one more to go. Draw the magnetic field due to wire 4. My magnetic field due to wire 4, it makes a big circle around wire 4. I want to draw that circle so it cuts through wire 2. Going to look something like that. To draw my magnetic field, I know it's going to be a tangent to the circle or perpendicular to the radius. The orientation of my circles is coming down this way. So I know my magnetic field is going to be down and right. It's going to be perpendicular to the radius, so kind of like that, B4. Your sketches don't have to be perfect, but you should try and get them in roughly the right direction. This is the diagonal of a square, so this angle is 45 degrees. This one's a right angle. This one is 45 degrees. These two are perpendicular, so this angle is 45 degrees as well. Okay, lots of angles there. All right, part A we've done. If we wish, we can copy it onto this picture if we want to get something to look at here. So B1 was up. B3 was left. And B4 was right and down. If you like them all on the one picture a little bit neater, there they are right there. We've got our coordinate system. Okay, part A is done. Part B, oh my goodness, do. Find the magnetic field at wire 2 due to each of the other wires. So now we're doing the vector sum of each of these magnetic fields to find the total magnetic field. Let's go back to our picture and find each of the magnetic fields on our picture. So B1 is going to have a magnitude of mu naught times I1 divided by 2 pi times R1. R1 is my distance from wire 1 to my point where I'm trying to find the magnetic field. That's at wire 2. So R1 equals A. We said that was 0.25 meters, 25 centimeters. I1 is the current flowing in wire 1. That was 350 milliamps. And then we'll put in our numbers. Mu naught is 4 pi times 10 to the minus 7 Tesla meter over amps times 0.350 amps divided by 2 times pi times 0.25 meters. Let's put that in the calculator and see what we get. 4 times pi times 1 exponent minus 7 times 0.35 divided by 2 divided by pi divided by 0.25 equals 2.80 times 10 to the minus 7 teslas. This is a vector. We should write it in unit vector notation. B1 equals 2.80 times 10 to the minus 7 teslas. Straight up, that's the y direction. If we're thinking about components of vectors, we'd say b1x equals 0, b1y, 2.80 times 10 to the minus 7 teslas. Okay, there's our b1. Next, we can do our b2. So for our b2, oh, sorry, I said b2, I meant b3. b3 is going to have a magnitude of mu naught times I3 divided by 2 pi times R3. R3 is our distance from wire 3 to wire 2. So R3 is equal to A, 0.250 meters. I3 is also 350 milliamps. So we've got 4 pi times 10 to the minus 7 Tesla meters over amps, 0.350 amps, divided by 2 pi times 0.250 meters, gives us the same magnitude we had for our B1, 2.80 times 10 to the minus 7 teslas. B3 points to the left, so that's a negative I hat direction. If we wanted to write down our components, we'd say B3x is minus 2.80 times 10 to the minus 7 teslas. B3y equals 0 because it doesn't point up or down at all. Okay, I think we got all that on the picture there. So the last one we want to do is B4. So B4, we'll use our same equation. B4 is mu naught times I4 divided by 2 pi times R4. R4 is the distance along the diagonal. So that's the hypotenuse of a right angle triangle where the two legs are A and A. So R4 squared is A squared plus A squared, 2 times A squared. R4 is root 2 times A, root 2 times 0.25 meters. Let's see what that's equal to. Root 2 times 0.25, 0.354 meters. Okay, I just want to try and tinker with the light a tiny bit here. There, I don't know if that's any better or not. The light is not so good in my office. Hopefully you can still see it. Maybe you can brighten up your screen a bit if you need to. Actually, if you can just pause for a moment, I'll turn back on my office lights. Hang on. Oh, I do think that's a little better. Sorry for the darkness. I hate the lights in this office. Okay, let's go before they click off again. So mu naught is 4 pi times 10 to the minus 7 Tesla meters over amps times I4. They all had the same current, 350 milliamps, divided by 2 pi times 0.354 meters. Okay, so we'll do that on the calculator. So there's our denominator. Multiply that by 4 pi times 10 to the minus 7 times our current. And we get 1.98 times 10 to the minus 7 teslas. This is a vector. The angle of our vector could be 45 degrees to the right of the negative y-axis. Or if we thought in terms of components, there's our B4x. There's our B4y. This angle is going to be 45 degrees because we have a right angle here. We already established that that's 45. So B4 is this at 45 degrees below horizontal. In our vector addition, we'd like to break this into components. b4x is equal to b4 times cosine 45 degrees. Okay, I'm not going to put that into the calculator. I'm just going to take this and multiply by cosine 45. 1.4 times 10 to the minus 7 teslas. b4y is negative because it points down. b4 times sine 45 degrees. I know sine and cosine are the same, so I don't have to do that in my calculator again. Minus 1.4 times 10 to the minus 7 teslas. Okay, so on the last three sides, we found the magnetic fields B1, 3, and 4. To solve part B, we need to do our vector sum. So part B, our net magnetic field is B1 plus B3 plus B4. Going to add them up as vectors. Bx is B1x plus B3x plus B4x equals. Let's get each of those slides going again. B1x is 0 plus B3x. My goodness, they're all sticking together on me. B3x is minus 2.8 times 10 to the minus 7. And then I want plus B4x. B4x is plus 1.4 times 10 to the minus 7. What I get for my total, minus 2.8 plus 1.4 is minus 1.4 times 10 to the minus 7 teslas. Okay, my y component, by, is b1y plus b3y plus b4y equals. b1y was 2.8 times 10 to the minus 7 plus b3y, where's my b3 gone? b3y was 0. And b4y is negative 1.4 times 10 to the minus 7. To give me plus 1.4 times 10 to the minus 7 teslas. Writing my answer as a vector, my net magnetic field B is the x component minus 1.4 times 10 to the minus 7 teslas x plus 1.4 times 10 to the minus 7 teslas j. So overall, the net magnetic field is a part to the left and a part up. Part B is done. Oops, my goodness. Did part B, that was on all those slides. And this part is C, went right on ahead and found the net magnetic field. Part D, find the magnetic force on wire 2. Okay, so wire 2 is a current carrying wire. We know the current. It's sitting in a magnetic field, so it feels a magnetic force. Let's write down our equation for finding magnetic force. Magnetic force, FB, is the current in the wire that's feeling the force, that's I2, times the length of the wire, crossed with the net magnetic field that the wire is sitting in. So this is of the wire, which feels the force, magnetic field that the wire sits in. Okay, let's put this together. So our current I2 is 350 milliamps. Oops, 0.350 amps. Our length of our wire is 3 meters. The direction of the length of the wire matches the direction of the current, which is out of the page. That's the plus K direction. So we're going to call that a K hat. This has to be crossed with the net magnetic field, which we found just a moment ago. So it's crossed with minus 1.4 times 10 to the minus 7 Tesla I hat plus 1.4 times 10 to the minus 7 Tesla J hat. Okay, now we just have to do that cross product. This is not so bad. First of all, let's multiply 0.35 and 3 together. 0.35 times 3, 1.05 amps times meters, K hat. That's going to be crossed with what we just wrote down for our magnetic field. Okay, let's apply some distributive property. I've got 1.05 times negative 1.4 times 10 to the minus 7. I get minus 1.47 times 10 to the minus 7. Amps times meters times Teslas gives us newtons. So this is my first term. This is going to be times K cross I. Then my second term is going to be this times this. So I've got plus 1.47 times 10 to the minus 7 newtons, K cross J. All right, now let's see what we get for these cross products. If you wish, you can use the little mnemonic for memory, I, J, and K. K cross I gives us J, and K cross J gives us negative I. So, and we'll write these in order. So we'll write this term first. Typically, you just write the I terms first. Then we've got this term. And now we're done. We wanted the magnetic force on wire 2, so we found that there in unit vector notation. Hopefully this will go together well with what we did in class, and this should make some more sense, maybe be a little easier to follow.